couple of minutes more, I suppose. Couple of minutes more, then we'll start.
So maybe before I start, on my side, the sound is not really good. Can you hear me well?
Yeah, I can hear you. We can hear you.
Okay.
Yeah.
Because on my side, it's a bit hushed. But,
okay. Now I was asking, how is the weather there?
Yeah, it's going fine. Yeah.
We are having our summer season here.
Aha. How is it?
And it gets pretty humid here because we are very close to the Ganges, this river Ganges, with lots of very humid and rains sometimes in the afternoon.
Okay.
So I think we can now
So are most of the participants in Calcutta, or?
What's that?
Most of the participants are in Calcutta, or
no, this is
from everywhere?
Online mode, and hybrid. Our students, around 30-40 students, are here in the campus.
Okay.
And the rest are all online mode all over India, and some from outside also.
Okay, very good.
We have approximately around 100 participants,
Mm-hmm.
Around 40 from here, our campus, who are offline, and 60 to 70 from outside.
Okay.
This is completely pan-India kind of outreach.
It was the same the previous years?
Yes. Okay, so I think we can start now. So it's a pleasure to welcome Professor Branciard to this platform. And as I was mentioning, he's not a stranger to this platform. He has earlier given talks, very enjoyable talks. He has, today's talk is about quantum processes with indefinite causal order. But if you look at his works, he has a very, deep interest and works on quantum correlations in general, non-locality, based on inequalities, quantum causality, indefinite causal order, and many of very deep aspects of quantum mechanics. Of course, today's talk is about indefinite causal order. It has created a lot of very interesting results. So today, we are the stage is with Professor Branciard. You have 50 plus 10, 50 minutes roughly for talk and 10 for question and answer. You can start your talk now. Yeah.
Okay, well, thank you for the very nice introduction, very kind. Hello, everyone. Good evening to those of you in India. I'd like to thank all the organizers also to give me this opportunity to talk here. So indeed, I will talk about a research area that I've been working on quite a lot in the last few years, which is this idea of having quantum processes with indefinite causal order. And I'm interested in particular in understanding how we can demonstrate this notion of indefinite causal orders in practice in some experiments where you may have trusted or untrusted devices, and there are different ways to do that. And this is what I will discuss here today. So let me start with a gentle introduction. So a bit more than 10 years ago, it was realized that just like quantum properties, position, momentum, quantum causal relations could also be indefinite in some kind of superposition. So and a famous example was proposed, that is the quantum switch, which is the one that is shown here. And that's a process where you have a control qubit here that will control the order of two operations being applied on some other system. So depending on the state of the control qubit, you apply A, then B, or if it's the other state, B, then A. And of course, if you start with a superposition of 0 plus 1 for the control qubit, you end up with a superposition of the two orders, and this is what we understand as some form of indefinite causal order. So it was realized that we could do some things like this, and we could play a bit with this, and then precisely in order to play with this kind of thing, there's a framework that was developed also about 10 years ago, which is the process matrix framework, which precisely allows us to formalize this idea of indefinite causal orders for quantum processes, even beyond this quantum switch. And this idea of indefinite causal order was formalized into the concept of causal nonseparability. That's the key concept that really identifies this notion of there not being any definite causal order in this framework. And now that we have this notion, then we want to certify in some experiment, or if you will give me a quantum process, whether it has this property of being causally non-separable or not. And there are different approaches for that. There are standard, the two main approaches that were first developed were a device-dependent approach and a device-independent approach that I will present. And here I'm also interested into going towards scenarios in between those two approaches. That's the quick introduction of what I will talk about during this talk. Maybe just a comment on the slide. So even if you're not working in this subfield of indefinite causal orders, well, you may still be familiar with some of the terminology that I'm using here. So non-separability, device-dependent, device-independent approaches. That's some terminology that is commonly used in quantum foundations, quantum information, when we talk about quantum correlations or non-locality. And indeed, there is some analogy with the study of quantum correlations in the context of entanglement of and Bell non-locality. So that's a nice analogy that I will come back to, but you can try to keep in mind this analogy to understand the terminology that I'm using and where I'm going to. So for this talk, I will introduce this framework of process matrices and this notion of causal non-separability. Then I will present the two standard approaches, which are device-dependent and device-independent approaches to certify causal non-separability. And then I will go to the scenarios that I mentioned in between the device-dependent and device-independent to try to find what can be done when you don't want to fully trust all your devices, but you also don't want to go to full device-independent scenarios. Also, I know that there has been a talk by Fabio Costa 2 weeks ago. So I'm guessing he already introduced the process matrix formalism. He's one of the main contributors and the initial authors of this. So this first part, at least, this is something that you heard already about 2 weeks ago, but please allow me to come back to it to remind you of all the basic concepts. It's always good to hear them several times. So let me start with this. So as I said, Fabio Costa was one of the main authors who developed the formalism, and this whole formalism comes from this paper by Oreshkov, Costa, and Bruckner, 2012. So the basic idea, the basic scenario that we're looking at is a bipartite scenario here, to make it simple, where two parties will apply some quantum operations. What do I mean by this? Well, they have some Hilbert spaces attached to some incoming system, to some outgoing system, and they will apply some operation between this incoming and outgoing spaces. A quantum operation is represented by a completely positive map, CP map, and the way we formalize the choice of an operation is through this idea of quantum instrument. So quantum instrument is a set of quantum operations of CP maps that can be applied. You cannot choose which of the CP maps in the set will be applied, in the same way as you cannot choose which measurement outcome you will get when you perform a quantum measurement. But you can choose the whole set, and with some probability, one of the maps here labeled by A, one of the maps will be realized. Okay, so we're looking at this situation where two parties apply some quantum operation, and then as usual in quantum foundations, we're looking at the correlations that can be established between those two parties. So that this quantum correlation is given by the probability of getting outcomes A and B. So that's the outcomes that correspond to which map of the instrument is actually realized, given the choice of instruments here. Okay. So we're looking at those correlations that are established for a given choice of operations by Alice and Bob, A, B here. And we are wondering, okay, how do we get those correlations? How do we get those correlations in a way that would be compatible, at least locally, with quantum theory? So these correlations should be, in some sense, at least a function of the quantum operations. The question we're interested in is how do we get those probabilities, and in particular, do we get those probabilities in a way where we can understand that A and B are in a well-defined causal order, meaning that either A acts before B or B acts before A. So more formally, this question whether there is a well-defined causal order between A and B is whether we understand A as acting before B, hence A can communicate to B, but not vice versa, or of course the other way around. So to warm up, let's start with some examples where we have this kind of situation with two parties performing some quantum operations. So basic example is the quantum state, where the quantum state would be shared between Alice and Bob. Here, Alice and Bob could perform some measurements. In general, this could be POVMs, positive operator valued measures. And that's the standard Born rule that you get that gives us the quantum probabilities for obtaining outcomes A and B for the POVMs chosen by Alice and Bob. As a function of there's a trace formula as a function of the quantum state. Of course, that's a non-signaling scenario, so this doesn't allow Alice and Bob to communicate. You can also look at a signaling scenario where Alice would communicate some information to Bob, so she could also send some quantum system to Bob through a quantum channel. And in this case, the probabilities would be obtained like by this. I can also write it as using a trace formula where I apply the channel from A to B on the state that is prepared by Alice, and then Bob applies the POVM. And you can play a little bit with the mathematics, and you can also write this formula in this form by introducing what we call the Choi-Jamelkovsky representation of the channel. So that's a way to represent operations. That's an isomorphism, the Choi-Jamelkovsky isomorphism between operations and states that is commonly used in quantum information, and that allows precisely to write this kind of expressions. Essentially, that's an isomorphism that translates quantum operations and turns them into quantum states, if you want, or into matrices. I will skip the details here. So anyway, in both the non-signaling scenario with just the quantum state or the signaling scenario with the quantum channel, I could write a trace formula of the same form. And in fact, what the process matrix framework tells us is that such a formula exists, even if you don't even if you don't assume a priori that there is a well-defined causal structure. When you pose that the probabilities you obtain in this scenario should just be a function of those quantum operations, then that's the general form of the correlations that you get. That's what we call the generalized Born rule. That unifies somehow the previous two cases, even without assuming precisely that there is a well-defined causal order, that one is before the other, or that there is no signaling. So that's the basic ingredient in the framework, that you can write such a generalized Born rule as a function of this object, this W, which we call the process matrix. So just to go through the details quickly, that gives us the probabilities again of obtaining measurement that are the results A and B for the choice of instruments of Alice and Bob as a function of the choice of instruments. That depends on the actual quantum operations, the CP maps applied by Alice and Bob, and some other object, W, which we also call a supermap, and I will not go into the details, but that somehow relates the two operations of Alice and Bob. That's the key ingredient in the framework. What is this W again? This somehow represents everything that is outside of Alice and Bob's labs, and that represents the way that they are connected. You could imagine that they're connected through some communication channels like this, but this can be more general. It doesn't have to assume a well-defined causal structure, no well-defined order between the operations of Alice and Bob. That's just a very general statement that you can also write the probabilities in this way as a function of this W. So because we don't want to impose this causal structure a priori, the way we usually represent this is in this form. So W just relates the operations of Alice and Bob without imposing a priori a causal structure. Okay, so that was a recap of a quick recap of the framework. Then we may want to understand a bit more about this W. In fact, the W, in some cases, the W represents some situations where there is a well-defined order. And in the previous two examples of the quantum state or the quantum channel, well, you could write a W that would correspond to these situations. And that would essentially correspond to the quantum state itself or to the quantum channel. So there are some process matrices, those W's, that are compatible with a well-defined causal order. The way we see this is because we will check for the probabilities, and we will see that those probabilities are only one-way signaling. So in this situation, if we see that all the probabilities that we get through this generalized Born rule do not signal from B to A, then indeed the W matrix, this process matrix, will be compatible with A acting before B. There is no communication from B to A, no signaling from B to A. And this can be characterized mathematically. So we understand those process matrices which are indeed compatible with a well-defined causal order, here from A to B or from B to A. We know how these look like, we understand these, we know how to characterize them. And then we can also make sense of some probabilistic mixtures of such process matrices, A before B or B before A. So one way to interpret the probabilistic mixture is that with some probability Q here, we will use this process matrix that connects A to B with A acting before B. And with probability 1 minus Q, we use another process matrix that connects B to A with B acting before A. So it's very easy to make sense of this kind of situation. And the process matrices that can be understood in this way, that do accept such a decomposition, we call them causally separable. Okay. And of course, the interesting thing is that there can also be some causally non-separable process matrices, so precisely process matrices that are not of this form, that cannot be decomposed in such a convex combination. These are the objects that we find interesting, because we cannot understand them as having a well-defined causal order, even with a probabilistic choice of the causal order. That's the interesting part of the formalism, that it allows for such causally non-separable process matrices. All right, let's give a couple of examples. So in that paper by Orshkov, Costa, and Bruckner that I mentioned before, where they introduced the process matrix formalism and they introduced this notion of causal non-separability, well, they came up with this example of a process matrix. They just wrote the matrix, and they showed that this is a causally non-separable process matrix. They gave some arguments that I will mention later, but essentially the claim is that you can write a process matrix that is perfectly valid in the framework, and that doesn't have this form of causally separable process matrices, which is causally non-separable. The thing is, it's only so far just a mathematical statement that this matrix is a valid process matrix and is not causally separable, but we don't really know what this matrix represents physically. So it's not very physical so far. Another example that is more physical and perhaps more interesting for us physicists is the one that I mentioned in the introduction, is the quantum switch. Okay, so the quantum switch is this process where, depending on the state of a control qubit, you will apply the two operations A and B in a given order, or in the opposite order. And indeed, this process, the quantum switch, can be formalized in the process matrix framework. So you can write a process matrix that represents the process. There's just a subtlety here, because to make it interesting, we need to keep track of the control qubit, and we need to introduce some third party in the future that will see the control qubit and that can measure it. So it's actually a tripartite situation now to make it more interesting. But in this tripartite extension of the framework that I introduced so far, indeed, the quantum switch is causally non-separable. So we now have a physical example that we understand, and for which we can really formalize this idea of having indefinite causal order, in the sense that the process matrix that represents it is causally non-separable. All right, so we have this framework now that allows us to calculate probabilities from the process matrices. So again, we get the probabilities as functions of the instruments, or of the quantum operations, and some other object W. And we can also just look at rather than looking at precisely the W and check whether it's causally separable or not, we can look at the correlations that can be established in this framework. So it's fairly easy to see that if W is causally separable, then looking at the correlations that you get with this generalized Born rule, you also get the same kind of decomposition for the correlations. So if you start with a causally separable process matrix that has this convex decomposition here, all the correlations that you get also have a convex decomposition into correlations that are compatible with A before B, where there is no signaling from B to A, and correlations that are compatible. Sorry, there's a typo here, with B before A. So no signaling now from A to B. Okay, and those correlations are called in this framework, these are called causal correlations. So these are the correlations that we're looking into this black box scenario. We don't really assume that we know what the boxes A and B are doing now. These are just black boxes. We're just looking at the statistics P of A, B given X prime. Yeah, so as I said, the causally separable process matrices can only generate what we call causal correlations. And of course, again, what's interesting is that there can be non-causal correlations. And indeed, there can be some causally non-separable process matrices that do generate such non-causal correlations. And this process matrix, first introduced by Oashkov, Costa, and Bruckner, that I mentioned in the previous slide, is precisely an example of a process matrix that can generate non-causal correlations. And this is how initially Oashkov, Costa, and Bruckner showed that this process matrix is causally non-separable, because it can generate non-causal correlations. But it's also interesting to note that not all causally non-separable process matrices can generate non-causal correlations, pretty much in the same way as not all entangled states can generate non-local correlations, can violate Bell inequalities. Here there exist process matrices which are causally non-separable, but still they cannot generate non-causal correlations. And unfortunately, the quantum switch is one of these examples. So the quantum switch, even if it's not causally separable, even if it has this property of causal non-separability, of being of having some form of causal indefiniteness, still it cannot generate non-causal correlations. So you cannot verify this causal non-separability of the quantum switch by just looking at the correlations. And this is actually the case for all of the quantum processes that are somehow of the same kind of the quantum switch. So we can generalize this idea of the quantum switch to more general processes. All the ones that for which we can give a simple interpretation in terms of coherent control of some orders. They will all be of this form. They can be causally non-separable, but they will not violate causal inequalities. They will not generate non-causal correlations. All right. So now that I introduced the general formalism of process matrices and causal non-separability, I want to tell you how to certify now causal non-separability. And as I said, I will first look at the device-dependent and device-independent approaches that were proposed through the use of causal witnesses and causal inequalities. And here, let me come back to this analogy that I mentioned at the beginning between entanglement and separable states on one side and causally separable or non-separable process matrices on the other side, local, non-local correlations on one side, and non-causal, causal and non-local correlations on one side. So there is this clear analogy between the two. And we can make use of this analogy to try to see how we certify things on the left-hand side, to see how we can do the same on the right-hand side. So for entanglement, well, the tools that were developed and the standard way would be to construct entanglement witnesses and to measure an entanglement witness. For local or non-local correlations, we typically look at Bell inequalities. And we characterize, for those who are familiar, we characterize the local polytope. And the very same ideas can be developed for process matrices and for certifying this property of causal non-separability. So we can build causal witnesses that can be measured to demonstrate causal non-separability. And in the case of non-causal correlations, we can also come up with causal inequalities. And that can be constructed by using a geometric approach through the construction of causal polytopes. So very briefly, because I'm realizing that I'm way too slow, I will recall those concepts. And I just want to emphasize that the top notions here are notions that are theory or device dependent. So that these represent really the physical resources. Their description depends on the theory, here quantum theory. And when you measure an entanglement witness or a causal witness, you typically need to trust what your measurement devices are doing. And here we are more into the black box scenario. These are theory and device independent notions. When you test the Bell inequality or a causal inequality, you don't need to know what the measurements are doing, what your devices are doing. These are device independent notions. So it's the same distinction as we make between entanglement and non-locality. Here we make it between causally non-separable process matrices and causal indefiniteness at the level of correlations, so non-causal correlations. Yeah, that's an analogy that is good to keep in mind. It's not too formal, so the mathematics behind are not quite the same. So we have to be careful that it can give you some good inspiration. So for instance, this idea of entanglement witnesses, the geometric picture is the one that we see here. So the idea is that the set of causally separable states is closed and convex. So if you take any entangled state, it will be outside, and you can also always separate it from the separable states by a hyperplane. And mathematically speaking, this translates into the existence of an operator here, S, where if you take the trace of it with rho for any separable state, it will be non-negative. And for the entangled state that you're interested in, you can get a negative value. That's a typical entanglement witness. And the very same idea can be developed for causally non-separable processes. So for any causally non-separable process, you can find such a hyperplane that is some operator that will give you a negative value when you take the trace for that particular causally non-separable process, while for any causally separable process, you get non-negative values. And the good thing is that this causal witness can be constructed efficiently via semi-definite programming, which is not the case for entanglement witnesses in general. And also you can measure, once you have constructed this witness, you can measure it by decomposing the witness onto some operations, applying those operations, and then combining the statistics to obtain the value of this trace. So you can measure this idea of causal, this tool, the causal witness, and then check for the sign of the trace. If you get a negative value, this certifies causal non-separability. This certifies that the W was causally non-separable. Okay, but because you obtain this the value of the trace through this decomposition and through those probabilities, these are device-dependent probabilities. So you know when you actually want to measure the witness, you need to make sure that your devices are actually performing the right operations. Looking at the other scenario with black boxes, where we just look at the correlations, that's again very similar to the case of Bell inequalities. So in the case of Bell inequalities, we usually talk about the local polytope. So the set of local correlations form a nice object that is called the polytope, and the same idea applies here. The set of causal correlations also forms a causal polytope, and the facets of this polytope defines what we call causal inequalities. Okay, so here's an example of a causal inequality. I will not go through the details, but essentially, we get some inequalities that tell us that all causal correlations are on one side of some hyperplane, and any correlation that violates a causal inequality is outside of the causal polytope, and hence is non-causal. So using this idea of causal inequalities, you can now certify causal non-separability if you get a violation of a causal inequality in a device-independent way, because here the correlations that we're looking at are just device-independent in the sense that we don't need to know what the measurements are doing. These are treated as black boxes. That's device-independent certification of causal non-separability. So let me compare the two situations. I need to speed up. The first one, device-dependent, is universal in the sense that you can build a causal witness for any causally non-separable process. But the drawback is that it requires full trust in the devices. The other side doesn't require any trust in the devices. Don't need to know what your devices are doing. The thing, unfortunately, is it's not universal. And in particular, the quantum switch, so probably the most interesting physical example that we have of causally non-separable process, the quantum switch doesn't violate causal inequalities. So now we're interested in looking into some scenarios in between. So we would like maybe to relax the assumption that we need full trust in the devices, because in practice you will not be able to implement perfectly the operations that you would like to. But maybe you don't want to go to the fully device-independent scenario, because then you cannot do much and you cannot certify the quantum switch. So that's why we're interested in those semi-device-independent approaches. And yeah, because I'm looking at the quantum switch, I'm also interested in this tripartite scenario where there is a third party at the end. So I will present two approaches that were proposed recently in the literature, and then show you how one of the approaches can take you to a fully device-independent certification. That would be the final slides. Okay, so the first semi-device independent approach that was proposed in that paper by Jessica Barbarasco and colleagues. And here the idea is that some of the devices are trusted, some are untrusted. So we call the trusted devices T, U for untrusted. And if you keep in mind this analogy with entanglement and non-locality, that would be somehow analogous to quantum steering, where only some of the devices are trusted, or one-sided device-independent approaches. So you can do this for the quantum switch in particular. So technically speaking, we like to see how robust to noise the quantum switch is. So we quantify the robustness when you add some white noise to the process that represents the quantum switch. And then we're looking at how much noise you can add to and still certify non-causality. So the quantum switch is causally non-separable. So if you trust all your devices, then you can certify the non-causality of the quantum switch, the causal non-separability. And using the terminology from this paper, they call it TTT non-causal. So trusted, trusted, trusted when all devices are trusted. And here you can certify some form of non-causality, this TTT non-causality. And of course, in the fully untrusted devices case, you cannot certify the non-causality of the quantum switch. So it's called UUU causal. And then you can look at the different scenarios where you trust some of them, but not all. I need to speed up, so I'll skip this. But essentially, there are some interesting scenarios in between where you can still certify non-causality of the quantum switch. And for instance, here you don't need to trust the last party. You don't need to trust one of them. As soon as you trust either Alice and Bob, you can still certify the causal non-separability of the quantum switch. So the other approach that I wanted to introduce is this semi-device independent approach with trusted quantum input. And the idea originates once again from this analogy with entanglement and non-locality. So if we start with a Bell scenario or the certification of entanglement, you can use Bell inequalities to certify entanglement, but not all entangled states violate Bell inequalities. Okay. But there is actually a form of non-locality that can be revealed by any entangled state. And this is the idea of that was proposed by Francesco Buscemi 10 years ago, where instead of having classical inputs for Alice and Bob, you have some quantum inputs. Okay, so you send them quantum states. Alice and Bob perform some joint measurements on the quantum input and the state that they want to certify. And using this trick, they can actually certify the non-separability or entanglement of any entangled state. So, and the way we can analyze this situation is by just putting all the untrusted parts in a black box. We're looking at the statistics of having A and B, given that we have those inputs rho X, rho Y here. And we can just look at the object that is formed by all the untrusted parts. We call it a distributed POVM. And by just looking at this object, we can certify the entanglement of the original state here. I'm sorry, I need to speed up, and I will skip the technical details. But essentially, the same idea can be applied to the certification now of causal non-separability. So instead of having a classical choice of instruments, then we can also use quantum inputs to those instruments by Alice and Bob, and keeping those instruments as black boxes. Okay, and the way we analyze this is pretty much the same. The thing is, we're looking at now the properties of this effective POVM. That's an effective measurement that is applied to row X and row Y. You can really understand everything inside as an effective measurement on those input states. And if W was causally separable, that implies some constraints, and W being compatible with a well-defined causal order, then these constraints translate into constraints directly on this measurement. Okay, and so this measurement will also satisfy some non-signaling. We'll also have some non-signaling properties. So you can just look at now at those properties of this measurement. Technically speaking, we define the notion of causal separability or causal non-separability at the level of the this effective measurement on the quantum inputs, and you can certify in this way causal non-separability by just looking at those effective measurements. And if you see that this effective measurement is causally non-separable, this implies that the W that you started with is also causally non-separable. So for those who are familiar with Buscemi non-locality, that's quite similar. And so causal witnesses can also be constructed for causally non-separable distributed measurements, distributed POVMs. And the question now is which of the causally non-separable Ws can indeed generate causally non-separable DPOVMs. In the case of entanglement, I told you that all entangled states could reveal their entanglement through this trick. This is not the case here, but at least all the Ws that violate the causal inequality can be certified this way. But there are also some processes that do not violate causal inequalities, whose causal non-separability can still still be certified in this way, and that's the case for the quantum switch. So the message here is that using quantum inputs, using the trick of Buscemi non-locality, you can now certify the causal non-separability of the quantum switch. Okay, let me skip all this. And now the last point I want to mention is that in the case of entanglement and Buscemi non-locality, this could be extended to make it fully device independent, or actually what we call network device independent. So that's using the idea of self-testing. We kind of self-test the quantum inputs. That allows us to make everything black boxes. Before we needed to trust the quantum inputs, and now we can have all the states, all the input states and all the measurement devices or all the instruments can now be untrusted. This idea was proposed in those two papers here for the case of entanglement, and now recently we tried to adapt the idea to the certification of causal non-separability. So essentially, the idea is that we start from the scenario with quantum inputs, then we use entangled state to prepare the quantum inputs remotely. And then using self-testing, we can self-test the preparation of the state, the measurement here, and that essentially certifies the quantum input here. So we don't need to trust anymore the measurement devices, the states here. So everything is black boxes now, and we can still have a fully device-independent certification of causal non-separability. We call it network device independent because we need to trust this network structure where we have independent sources and the process in between. There is this structure that we need to trust, but once you trust the network structure, this is fully device independent. All right, final slide. Just to mention that there was another work that also proposed a fully device independent certification of some form of causal indefiniteness. There were actually two papers that proposed very similar ideas. The idea here was to combine some assumption of definite causal order and locality, although this assumption of locality is weaker than the assumption of Bell locality. It's just parameter independence. technically speaking. And if you assume those two assumptions together, then you can come up with inequalities. So here they called these local causal inequalities that now can be violated by the quantum switch. So the assumptions are stronger than for just causal inequalities, but here you can get inequalities that can be violated by the quantum switch. So you can now certify in a device-independent manner also the non-local causal property of the quantum switch. So you violate the joint assumption of definite causal order and locality using this kind of technique. So it's not quite certifying the causal indefiniteness of the quantum switch. It certifies the violation of those two assumptions together. But that's interestingly, that's a device, and actually even more strongly, a theory independent certification of indefinite causality if you assume locality. I wanted to make a comparison with our proposal, and I will be very quick about this. So actually, both proposals allowed for some form of device-independent certification of indefinite causality under some different assumptions. So here, the additional assumption was some locality assumption. Here we have this network structure. But essentially, in both cases now, you can certify some form of indefinite causality under some additional assumption in a device-independent way. Both use a trick using some entangled states, as you see here. I didn't go into the details, but you entangle the control qubit to another party. Here we use entangled states that are given to Alice and Bob, so we don't use those additional entangled states quite in the same way. But now it would be interesting to see what we can do by combining the two kinds of scenarios and using entangled states in different ways in both scenarios. Okay, I apologize. I had to go very quickly at the end. I will just leave the final slide here, and I will stop here and take questions if you have any.
Yeah, Dr. Ranjit Singh, you can unmute and ask questions. You have some questions, please ask. Dr. Singh.
Should I read the question or?
Yeah.
Okay, so Ranjit Singh asks, okay, he's on a local bus. So the question is, when I calculate mean values over time in quantum mechanics, then I will see the same behavior of mean value curve if I rerun my calculations again and again, and the same initial conditions for a conservative system. The question is, what do you mean by indefinite in quantum mechanics and in quantum causal orders? Or could you please provide definitions of terms indefinite in quantum mechanics and causal orders? Well, this process matrix formalism that I presented and that was introduced by Rashkov, Costa, and Bruckner, that Fabio Costa also presented 2 weeks ago, that's precisely the formalism that allows us to formalize this idea of indefinite causal order. Okay, so we provide a definition of indefinite causal order as the opposite of definite causal order. Definite causal order is this situation in the bipartite case where you can say for sure that one party acts before the other, or the other way around, or where you have a convex mixture of the two, meaning that with some probability, with some classical probability, you get A before B, and with the opposite, the complementary probability, you get B before A. If it's just a classical mixture of those two, we say that this is a definite causal order, okay? And then indefinite causal order in this framework is defined as any situation where you cannot give this decomposition into a classical mixture.
May I ask a question?
Yeah, please go ahead.
Yeah, it might be a bit technical one. So you talked about Buscemi non-locality. So what is the idea there, that you use an entangled state, and how does it help to satisfy the given entangled state?
Right. So then the key thing to realize is that you will use quantum states that are indistinguishable. Okay, you use sets of quantum inputs that are not fully distinguishable. So you cannot just measure the state here and determine which state it was. Okay, otherwise this would just be equivalent to having a classical input. And because there is this indistinguishability in the quantum inputs, it turns out that you can translate any entanglement witness into a witness in that scenario. Okay, so as I said, that the way we do it is by looking at this object. So we put together all the untrusted parts. So we don't need to trust the measurement devices. So we also call it measurement device independent. So we don't need to trust the measurement devices. We don't want to trust the physical state, because that's what we want to certify as being entangled. And then we see that this whole object acts as an effective measurement on the quantum inputs here. Okay.
Okay, so you are trusting rho x and rho y, right?
Yeah, at this point we trust rho x and rho y.
Yeah.
And we use this precisely to reconstruct this object, EAB. In the case of entanglement, it turns out that the entanglement somehow gets transferred onto this object. And by characterizing this object, we see that the initial state was entangled.
Okay, and these input states are like single qubit or single system.
Yeah, at this point, these are single systems, yes. But indeed, as you see in the quantum inputs. So at this point, we need to trust the quantum inputs. And then when we extend it using self-testing, this allows us to relax this assumption of trusting the quantum inputs.
And in the network scenario you talked about device-independent causal order. Here, your input states were also single system states, or they're different?
Yeah, here it's really the same kind of scenario. We use single quantum systems given to Alice and Bob. And again, the causal non-separability of the W somehow gets transferred onto the effective measurement that is applied to those quantum inputs.
Thank you.
I have a question. You mentioned about quantum sortings. So does it mean there are some tests one can do experiments? There are some experiments exist in this area?
Yes, yes, absolutely. There has been quite a few experiments now realizing a quantum switch. So pretty much all experiments were realizing a quantum switch or slight variations of a quantum switch. So one experiment was implementing a 4 switch with 4 parties, but essentially the same kind of ideas as the quantum switch. And yeah, there has been quite a few experiments, more than 10 experiments now, realizing a quantum switch, and then either directly testing a causal witness or demonstrating some advantage. So I didn't mention that, but those processes with indefinite causal order allow for some advantages for quantum information processing tasks. And so some of the experiments were proofs of principle experiments for demonstrating some possible advantage of the quantum switch.
Thanks.
As there is still time, I want to ask a question.
Okay. Yeah, go ahead.
Okay, I'm asking first, then Varun, you may ask. So, so these non-causal resources, they are talking about non-separability in time, in a sense, right? Like the indefinite causal order, which is
in some sense, although we don't talk about time. I mean, there is just no causal structure, no time defined outside of the other labs. But yeah, somehow this is related to non-locality in time.
Yeah, but can they generate some spatial non-locality, these non-causal resources? Has it been studied, or is it at all possible?
Well, it generates non-causal correlations.
Non-causal correlations or some non-causal.
This form of non-locality in time. That's the form of non-locality in time. If you wish to make a make a connection.
But can they generate some spatial non-locality like Bell's inequality? Can they help, or can they generate those type of spatial correlations? This non-causal resources as like quantum states.
So quantum states are particular examples of processes, and actually of causally separable processes. So entangled states are some particular cases of those. So anything that can be obtained from an entangled state can be obtained from process matrix, although it will not use the causal non-separability of the process matrix. So you're asking whether using a causally non-separable process would allow you to get some stronger form of non-locality or something like that.
Yeah.
Yeah. You would need to look at some specific form of non-locality that you're interested in, and look whether you can get some more by using causally non-separable processes. And there could be a connection with this work where they define this notion of local causality, although it's not the same as Bell's local causality, but they use the same terminology, unfortunately. And here they show that indeed causally non-separable processes allow for some violation of this kind of inequality. So here you get indeed stronger non-local causality for their terminology than with standard causally ordered processes.
Okay. And here, when you say causal inequality, is it the same inequality that was used in the 2012 paper by Costa Bruckner?
This inequality here.
Yeah, you say when you say some device independent certification, it violates some causal inequality.
Yeah,
and is it the same?
No, that's what they call a local causal inequality. So the assumptions behind are different. The assumptions under which you derive those inequalities are different from just the assumption of causal correlations, and the inequality is different. And it looks a bit the same, and actually it's constructed based on same ideas, like this guess your neighbor's input ideas, but the inequality is different. So somehow you can understand this inequality as combining somehow a guess your neighbor's input inequality and a Bell inequality.
Thank you.
Are there any more questions?
Yeah, I wanted to ask. So my question is somewhat related to what Shomik just asked. We know that there is some correspondence between multi-time processes and multi-body physics, right? In some cases, you can sort of get a mapping from these two cases. So does causally non-separable process matrices have any analog to any multi-body physics?
I'm not sure what kind of connection you're looking for. Indeed, we can extend the whole formalism to multipartite scenarios.
Yeah.
And then the notions of causal separability, causal non-separability become more slightly more complex. But you can extend all this. But then I'm not sure what kind of connection you're looking for.
No, I just wanted to ask, is like a multi-time process for some scenarios can be translated to a multi-body scenario. I think this is some work of Kavan Modi's, in which they have showed that using process tensor formalism, that if you have a multi-time process, you can translate that into a multi-body scenario. So I was just asking, if I have a causally non-separable process matrix, is there any is it possible to translate it into certain multi-body scenario, and is there any analog to that?
I'm not sure how to answer. So I don't know the details of how Kevin Modi made this connection and whether this would still apply to causally non-separable processes.
Okay.
I'm guessing it would not apply directly.
Okay. And I have one more question in this slide only. So you said there is an assumption of locality in this device independent while approach.
Yes.
What can you like explain that? What exactly is that?
So this is what is called parameter independence in the standard literature on Bell non-locality. So it's a weaker assumption than Bell's local causality. Otherwise, of course, it would be much less interesting. So that's parameter independence. You can understand it as no signaling at the ontological level. So even at the hidden variable level, there should be non-signaling somehow.
Okay, so the measurement inputs and the outputs are independent of.
Yeah, it's a form of no signaling between the two Alices here and Bob and Charlie as well, if I remember the details, even at the ontological level.
So does that mean that like there is no non-local correlations?
So that forbids no, sorry, what did you ask? That means it still allows for non-local correlations in the sense of violating Bell inequalities.
Okay, so this inequality was derived assuming definite causal order and locality. So if the inequality violates, so if the inequality violates, how can you certify that it's actually indefinite causal order? It can be non-locality as well, no?
Yeah, precisely. Yes. So it doesn't certify by itself definite causal order. It certifies definite causal order if you assume locality.
Okay.
So it's certainly a weaker claim than certifying indefinite causal order of the quantum switch. A weaker claim that you could make with a causal inequality. But essentially the result is that by adding some additional assumption, some form of locality, then you can come up with a device independent test where you can draw some conclusion. And the conclusion is if you accept the idea of locality, then you have to abandon definite causal order. But indeed, it could be locality itself that is violated, absolutely.
If there are no more questions, let's thank Professor Branciard for